thanks for the intro. Our project is looking at biocomposite design for food packaging. And a lot of this probably you will already know, but just to emphasise the motivation for our project, we've got over 1 million tonnes of packaging films entering the UK waste stream each year. And most of these films are single use, with only about 5% of local authorities actively collecting and reprocessing these films. And the low recycling rates of films is a number of factors. We've got limitations in current recycling infrastructure, and also when it comes to food packaging, we've got frequent contamination with food residue, making recycling really difficult. But we all know that packaging films help to prolong the shelf life of food, and so they help to reduce food waste. So we don't want to lose them altogether, but we think that more of these films should be compostable and made from sustainable sources. So conventional sort of oil-derived plastics have benefited from, I guess, just short of a century of research and development, whereas compostable plastics are a lot newer, so they've not seen these sorts of R&D efforts just yet. And as a result, their properties aren't quite as optimized as we'd like them to be. So some of the kind of key properties for food packaging films, we want good mechanical strength and flexibility. We want the plastic to be a good barrier against certain gases like oxygen or carbon dioxide and water vapor, which is crucial for preserving the food inside. And we want them to be melt processable. But we can improve a lot of these properties with adding things like filler particles or plasticizers. But we need some design guidelines to help accelerate this transition to sustainable plastics. So it's the formulation of the polymer composite which controls the crystallinity and the microstructure. And then in turn, the microstructure controls the film performance. So we want to better link the formulation to the film properties and its behaviour. And so our aim is to design sustainable, compostable and industrially processable polymer composites to help facilitate the shift away from oil-derived plastics, which are being used for packaging films at the moment. So a lot of our work is focused on polyhydroxyalkanoates, or PHAs, and these are a family of polyesters which are sourced from bacterial fermentation, and they can be produced from fermentation of food waste or agricultural waste, which at the moment doesn't really have much market value. We've got a variety of monomers that are available. So throughout the talk, I'll be referring to PHB, which is polyhydroxybutyrate, but you can also make copolymers using a sequence of different monomer units. PHAs are compatible with existing melt processing technologies, so they can be kind of scaled up and produced at larger quantities. And they are fully compostable, which means that for polymer composites, any additives that we use, any fillers or plasticizers, should also be compostable and safe for contact with food. So this is our research group here. We've got a mix of kind of modelers and experimentalists to give a combined approach to the problem. So we use computer simulations, in particular molecular dynamic simulations, to help understand how filler particles and plasticizers affect the polymer crystallization behaviour. And then we also are doing a lot of experimental work to look at the effect of processing conditions and additives on the crystallization, the microstructure and the film performance. And we're combining these results to create design guidelines to enable the faster development of sustainable plastics. And so this is the polymer model that we use in our simulations. It's called a Kramer-Grest generic polymer model, so it's not specific to any one polymer as such, which means this model can be used to look at the melting and crystallization behaviour of a number of polymers, such as polylactic acid, for example. So we've got our polymer chain, and to that we can also add plasticizer molecules, and we can add a surface, which is representative of adding a filler particle. And then we can tune things like the chain stiffness to give a more stiff or more flexible chain. And we can also tune the interaction strength between the polymer and the filler surface. So I'll talk through some of our results now. So if we have a bulk polymer system, so we've not got any surfaces in there, no filler particles, then as we cool the system down, we get a very, very small increase in crystallinity. And the way we measure crystallinity in the simulations is by counting the number of straight segments of the chain. So that's kind of thought of to be the first stage of polymer crystallization. So you'll see there's some kind of randomly orientated straight segments in the amorphous matrix. However, when we add a surface, which is, like adding a filler particle, then we have a more significant increase in crystallinity. And here we can also see the growth of crystalline regions growing at the filler surfaces. And so we know that it's the presence of the filler surface which promotes the crystallization. And so experimentally, we see something similar. We find that when we add a filler particle to PHB in the form of a sort of fine powder, then these fillers act as nucleation centers, which leads to the formation of lots of small spherulites, which are these crystal structures here. So this one on the left, that's pure PHB, and that's just one kind of giant spherulite that we see. And then when we add 1% of filler, we have a few spherulites in there now, and then 5% filler, we've now got a much higher nucleation density because those fillers are acting as nucleation centers. So I mentioned we can also tune the interaction strength between the polymer and the filler surface. So from our simulations, we see that as we increase the interaction strength here, going from light blue to dark blue, then the temperature at which crystallization occurs on cooling shifts to higher temperatures. And simultaneously, we see an increase in the overall crystallinity of the polymer. And this is consistent with experimental observations. That's the image on the left and the right, they're the same concentration of filler particle, but they're just different types of filler particle. And so we can see that the nucleation density depends on the chemistry of the filler, because different fillers are going to have, depending on their functional groups, will have different interactions with the polymer chains. And so as an increased nucleation rate will show us an increase of nucleation sites, and so the spherulites will be smaller. So now on to plasticizers. So from our simulations, we see the opposite effect with plasticizers. This time, as we increase the concentration of plasticizer, going from right to left here, the temperature at which crystallization occurs actually shifts to lower temperatures now. So we've got a lower crystallization temperature and simultaneously a lower degree of crystallinity. So in these diagrams here, this is snapshots from our simulations, and we've got the crystalline polymer, the straight segments shown as the, you can't quite see the key at the bottom here, but that's the blue spheres, and then the purple ones are the plasticizer beads. And for visualization purposes, we've not shown amorphous polymer here, it's just the crystal regions. So we can see that as we increase the concentration of plasticizer, the size of the crystal regions at the bottom, they decrease. And I've got a video. Hopefully it plays. Okay, it's a bit laggy, but we can see the growth of the ordered region at the bottom. So this is our filler surface at the bottom, and you can see this crystal region grows up from the bottom, and as it grows, the purple spheres, the plasticizer molecules, are actually expelled from the crystal region, and this leads to a higher concentration of plasticizer that's left behind in the amorphous polymer. So experimentally, we find that when we add plasticizers, we have the number of spherulites decreases, and these spherulites can actually grow larger. So taken, for example, at 70 degrees, the pure PHB system has over 300 spherulites present in one window, whereas when we add 10% of triacetin, which is our plasticizer, that falls to about 130 spherulites, and then increasing further to 20% triacetin, we've only got about 25 spherulites. So we find that more plasticizer leads to fewer spherulites. However, these spherulites have more space to grow larger. And just like in our simulations, we find that experimentally, when we add plasticizer, the temperature at which crystallization occurs drops to lower temperatures. So pure PHB is a crystallization temperature about 79 degrees, and then by the time we've added triacetin, that can fall to around 67 degrees. And that's because the plasticizer molecules increase the free volume in the system, and more flexible chains need lower temperatures to crystallize. And so we wanted to measure the barrier properties of these films, and to make films which were thin enough for barrier testing. We couldn't use melt processed films because they were too thick, so we've dissolved PHB powder and added any fillers or plasticizers, dissolved that in solvent, and then cast that using a casting blade onto a glass support. The blade moves across, and the solvent evaporates pretty rapidly, and it leaves behind a very, very thin film of PHB, and I have one here just to demonstrate. This is a very thin film. It's only about 20 microns thick, and that is the sort of thickness that we need to be able to test the barrier properties. And so this is how I've done it. I've sealed a piece of PHB onto a glass vial of water, placed those vials into a dry environment to help drive that permeation. And then got some results here. So I've got PHB in the middle, and just for comparison, I've got a couple oil-derived polymers and then a couple compostable polymers. So when we compare PHB, the water vapor transmission rate to, for example, PET, we find that the permeation through PHB is about 10 times higher than PET, which doesn't seem great. However, when you compare to for example, PLA, the most commonly used compostable polymer at the moment, the barrier properties of PHB is actually much stronger. So as James mentioned, the lower the permeation rate, the better. And this is quite crucial for talking about food packaging, and if we want to preserve foods which are sensitive to moisture, then using PHB is actually, looks to be a better, more efficient than PLA or polycaprolactone. So for our PHB films, we've identified some promising formulations. We've found that boron nitride is a good filler because of the epitaxial match with the PHB crystal. We found triacetin to be the most effective plasticizer that we've looked at. And triacetin is also compostable. It's safe for contact with food, and it's quite inexpensive as well. And we found that I mentioned we have different monomers available, and we can produce copolymers. We found that if we add valerate monomers to produce a hydroxyvalerate copolymer, then we end up with lower spherulites and lower degree of crystallinity. And so we've got different films made different ways here. So previously we looked at films that had been melt pressed. We've also got films which were melt extruded using extrusion equipment at Queen's University Belfast. So these were done at quite large scale to show that PHB is compatible with existing processes. And then we've got our thin kind of solvent cast films as well. So most studies which look at PHB, they correlate its performance just with the overall degree of crystallinity, but very few actually delve into the microstructure of the film. And films produced in different ways will end up with different microstructures as well. So just some ongoing work we've got at the moment. So we're testing the mechanical properties of PHB. We've got a new sort of tensile testing machine set up in the lab, so that's kind of coming next. We're linking the water barrier to the microstructure, and we've got a collaboration ongoing with James at Cambridge Uni to look at coating cellulose with PHB to further improve its water barrier. And then we'll use these trends to build design guidelines for compostable packaging. And note that there may be a trade-off between properties. So at the moment, it seems like a coarser microstructure, larger spherulites, is better for improving the barrier. However, this might end up hindering the mechanical properties. So it's just like a fine balance between the properties when we're looking at specific applications. And so just to sum up, we've identified some really promising fillers and plasticizers for PHB. We've got simulations which capture the experimental behavior and help us to connect the material interactions with the nucleation behavior. Found that filler particles lead to lots of small spherulites, whereas plasticizers lead to fewer but much larger spherulites. We've established that the water barrier of PHB film is actually pretty good when compared to other compostable polymers, and we've got mechanical testing underway. So just some acknowledgements. Thank you so much to the SSPP funding, made this project possible. Strathclyde Uni Research Excellence Award for funding my PhD, and the computational resources provided by the Archie West supercomputer. So thank you all for listening, and welcome any questions.